Here we are again. We are on the last rule that we're going to learn, the last of the derivative rules. This is the chain rule. Now here's what I want to say about the chain rule. I want to say a few things. The first thing is this, is that the chain rule is a favorite. Lots of math people really love the chain rule. And there's a good reason for loving the chain rule, because the chain rule comes up all the time in calculus. The chain rule is a part of the explanation for why we do a lot of the things we do in certain kinds of problems. So the chain rule is extremely important. So if you're going to know only one of the rules, that's a bad idea. Don't only know one of them. But if you were only going to know one of the rules, it better be the chain rule. But let me tell you something. If you don't know the other rules, it's not really going to matter. So listen, the chain rule is a favorite. We love the chain rule because it's extremely useful. Now, here's the other thing. The chain rule, in my opinion, the chain rule is the easiest one to remember. It's easier than the product rule. It's easier than the quotient rule. Okay? Now, you're not going to think about it that way at first. And probably that's because, well, most of my students, the problem is a lot of people, they don't know when to use the chain rule. It's not that they can't do the chain rule. They know the chain rule. It's just that they don't know when to apply the chain rule. They see a situation and it looks like multiplication, so they try to apply the product rule. But it's not. It's a chain rule problem. Well, what is the chain rule? When would you use the chain rule? You're going to use a chain rule when you're dealing with what is called a composition function. A composition function. What that means is you have a function inside of a function. You have an inside function and you have an outside function. And it's important for you to understand which one is the inside function and which one is the outside function. Now, a lot of times the inside function is actually inside of parentheses, and that makes it a lot easier. But a lot of times there aren't parentheses around the inside function, and so it's harder to see. But here's how I do it. I want you to watch this. So composition function looks like this. You'll see y is equal to f of g of x. And you've probably seen that before, or maybe you haven't seen that before. Here's what happens. Where you would normally just see an x, normally you just see f of x, right? This doesn't say f of x. You see more than just x. See, there's more than just x here. It's g of x. It's f of g of x instead of just f of x. So, wherever you would normally just see x, if you see something different than x, it's a chain rule problem. Let me show you an example. So let's say that we have a function. Let's say it's y is equal to e to the power of x to the third power. That's a little weird. We have an exponent that has an exponent. That happens all the time in calculus. Now watch this. When we see this function e, don't we normally see it as y is equal to e to the x power? It's normally just e to the x. We normally, in the exponent, just see x. But in this case, it's not just x. It's x to the third power. And because we don't see just x, we see something different than x. This is a chain rule problem. Let's look at another example. How about y is equal to the natural log of 4x, the natural log of 4x. When we see the natural log function, don't we normally just see y equals the natural log of x? Isn't that what we normally see when it's a natural log function? But this time, it's not the natural log of x, it's the natural log of 4x. Therefore, this function for the derivative is going to require the chain rule. Okay? Let's look at a couple other examples. What if we had y equals cosine of 7x to the third power? What do we normally see here? Don't we normally just see cosine of x? But this isn't cosine of x. It's cosine of 7x to the third. Instead of just seeing x, we see something different than x. Therefore, this function is going to require the chain rule. Let's do one or two more examples. How about, what if we had y is equal to sine inverse of 2x to the 7th power minus e to the x plus 5. That's pretty crazy, isn't it? It's really crazy looking. Look at this. Normally we just see sine inverse of x. But now we have sine inverse of this trinomial weird thing with polynomials and exponents, right? Because we see something different than just x, this problem is going to require the chain rule. And let me show you how we have an inside function and an outside function. This piece right here, this is the inside function, and sine inverse, that's the outside function. We have an inside function and we have an outside function, okay? So that's what I want you to remember, that we have an inside function and an outside function, and then I'm going to show you how to do the chain rule, okay? So let me get rid of this and we'll come back. We'll come back to this. I'm going to write over here the way I understand it. The way I understand the chain rule is I have y is equal to an outside function of, with parentheses, of an inside function. Okay? We have an outside function with another function put inside of that function. Okay? So this is going to require the chain rule. And here's how the chain rule goes. dy dx, or y prime, is equal to, now ready? I'm going to say it first, and then I'm going to write it down. Okay? Here's how it goes. Now I do want to remark, it's not as simple. You don't just do the derivative of the outside and then the derivative of the inside. That's not how it works. Just like the product rule and the quotient rule, it's not what you think. It's more complicated than that. But this is still pretty easy. Ready? First, you're going to do the derivative of the inside function. So we're going to do inside prime times the outside function of, or prime, the outside function prime of the inside function. Here's what I mean by that. First, you're going to do the derivative of whatever function is inside the function. Then you're going to multiply that by, you're going to do the derivative of the outside function. But when you do the derivative of the outside function, it's not going to be of x or of some derivative. You are going to take the unchanged inside function and put it as is inside of the derivative of the outside function. Okay? Let's do an example, shall we? Let's say that we have y is equal to 3 to the power of sine of x. Let's say that this is our function. I know it's kind of weird, right? And this would probably make a pretty interesting function to look at. You can plug it in a graphing calculator. Okay, but let's find the derivative. Normally, we would just see 3 to the x power, but this doesn't say 3 to the x power. This says 3 to the power of sine of x. So, the inside function is sine of x. The outside function is 3 to the x power. So one way of knowing what the outside function is cross out or sort of cover up the inside function and just put an x there. And that's what the outside function would be. If we got rid of the sine, if we got rid of this and just put an x there, it would be 3 to the x power. So that's what the outside function is. It's an exponential function. So we're going to have to do the derivative of an exponential function. So we got 3 to the power of sine of x. So let's find our derivative here. Y prime is going to be equal to, the first thing we're going to do is the derivative of the inside. Well, the inside function is sine of x. What's the derivative of sine of x? Cosine of x. So it's going to be cosine of x times, right? Derivative of the inside times the derivative of the outside. Now, the derivative of 3 to the x power is 3 to the x power times the natural log of 3. So, 3 to the x power, but I'm not going to put anything there yet, times the natural log of 3. So that's the derivative of the outside. And now, instead of putting an x in the outside, in the derivative of the outside function, instead of putting an x here like we normally would, we're going to put the original inside function, which is sine of x. So it's going to be 3 to the power of sine of x times the natural log of 3. Let's do another example. All right, so what we have here is f of x is equal to cosine of 5x squared. Okay, so normally we would have cosine of x, but instead of cosine of x, we have cosine of 5x squared. 5x squared is different than x, so we must need the chain rule. So if we want our derivative, we're going to do f prime of x is equal to derivative of the inside. Well, what's the inside function here? 5x squared. What's the derivative of 5x squared? 10x. So 10x times the derivative of the outside. Well, what's the derivative of cosine? The derivative of cosine is negative sine. Now, I'm not going to put, watch what, you got to be careful here. I'm not going to put negative sine here, right? Because we're multiplying by negative sine, I'm going to put the negative on the front, because a positive times a negative is a negative. So it's going to be negative 10x, then sine, okay? So this is negative sine. And then, instead of putting sine of x, I'm going to put the inside function, unchanged. What is the inside function? It's 5x squared. So sine of 5x squared. So what you can see here is, this is the derivative of the inside times the derivative of the outside, negative sine, of the inside unchanged. And that's the chain rule, okay? This is going to take a lot of practice, but I promise you, when you do the chain rule, when you practice it a lot, you'll get really good at it and you'll start to notice it, and then it'll just be second nature to you.